All right.
I have visual aids.
That's not funny, Idris.
Okay, Kramer, did you write this one down?
I have not.
Everything is futile.
After
Sit up, right now.
Everything
Get on
is
the pen. Sit up and skate
I'll actually take it back.
Keep it
That's called future wife.
What really is the purpose of this board right here? What is it connected to?
It used to have a projector,
Oh, one of those
laminated.
The thing where you put the stuff on it.
Yeah, like that big thing that you hang down. All right. Hey guys, let's begin. Okay. So obviously earlier in this chapter we've been spending a considerable amount of time talking about uniform circular motion. What is that? Going in a circle. Okay, one person. Go ahead, Bryce. Okay, going in a circle, but be more specific.
At the same
At the same speed. Okay. So your speed is not changing. Okay. All right. It says during uniform circular motion, an object is going to move in a circular path at constant speed. So let me ask you a few questions. If you're moving at constant speed, raise your hand if you can tell me why the object is accelerating.
One person.
If you're in uniform circular motion and you're not speeding up, how can the object accelerate? Lauren? Constantly changing directions. At any point in that motion, there is no way to not change directions if you're going in a circle. Okay? Next, raise your hand if you can define what this acceleration is called. What's its name? Bryce. Centripetal acceleration.
There we go.
Okay? Where is the acceleration directed? Raise your hand. Cole.
Towards the center.
Towards the center. What force is causing the motion, and in what direction is it directed? Go ahead, Lauren. Centripetal force, what do you mean by a force? Yeah, the up and down things cancel out, so your centripetal force is always directed toward the center. Okay? So in this particular in this particular section, we're going to start talking about rotational motion and how torque is involved in rotational motion. I've never had anybody do anything circular.
We can do.
We're gonna do it.
Oh, you have a skateboard. Okay, I lied. If you count that as circular motion, then that's.
I know it was
I'm talking about like actual.
Oh, the roller coaster.
Okay, yeah.
I was thinking of like something like a a Ferris wheel type of circular.
Oh,
That's
If we can make a Ferris wheel.
You guys can do whatever you want.
we should do a Ferris. I thought
Hey guys, we're stealing the adventure.
Honestly, guys, the thing that makes the Rube Goldberg machine the best is the most unique stuff that you guys can bring.
Yeah, the more unique, the more chance for a better.
Well,
Yeah, exactly.
yes.
Because you're risking.
Unique also informs. There's a difference between unique and weak. Whoa.
We're gonna make it weak.
Like, there's most of the time the reason why people aren't successful in being unique is that they didn't solidify it enough that it would be consistent enough to do the same thing as mine.
So you're saying.
We're gonna sabotage the day before.
But also remember that the more tests you do, the more Murphy's laws will break things down.
So what if you see it? What if you see it work a bunch of times throughout the day of the actual grade for it?
Murphy's law, man.
Oh, okay.
There's no happiness.
That is unfortunate, and I hate that.
That's more than unfortunate.
That is pretty unfortunate. Yeah, absolutely.
I'm gonna do
That's so all that happens, yeah. It's all.
But we will talk about that the day after Christmas break. that's when we will get you guys started on that. Okay?
All my spare time is going.
Okay, so rotational motion. So here they talk about two types of motion, rotational motion and translational motion. Rotational motion is what it sounds like when you're what? Rotating. Okay, translational motion is straight line motion. Okay, so they go on to say that you can analyze these separately. They give you an example of when a bowling ball strikes the pin could move straight back, but the pin could also what? Rotate, right? So you can have both types of motion in the same process. Thankfully, we're not going to do the difficulty of doing both of those together.
What was bowling ball?
When the bowling ball hits a pin, the pin can move straight back, but the pin can also be rotating.
At the same time as moving back?
Yes.
Oh, okay. I thought you just meant to start spinning after that.
That's why.
That's only one.
Oh, yeah. The bowling ball hits it, just starts.
So it says in this section we're going to isolate rotational motion for various reasons. The same reason why we do everything in a vacuum and with no friction.
Makes it practical.
Makes it practical. Yes, makes it easier. Okay. So really, what we're going to study in this particular section is the ability of a force to rotate an object, aka torque. Okay. So let's progress. Oh, wow, that's a lot. There is your torque equation.
Sign of theta.
In the note packet it says sign of Q.
It says Q?
Yes.
No, I'm guessing it
No,
autocorrected.
in the book, yeah, they're saying in the book it says theta.
Yeah, it's
But
theta.
in there it's-
I might have tried to put theta and then it's autocorrected to Q.
It also is interesting that that torque is FD sin theta, but work is FD cosine theta.
That's what work is.
Yeah.
Light or?
I never made that connection.
What connection?
That work is FD cosine theta.
Yeah, it's the exact same as work except for sine and cosine are different. Interesting. Okay, so really what torque is, guys, in a nutshell, torque is really just the ability of a force to cause an object to rotate. More torque, more rotation. Less torque, less rotating. Okay? What? What? It's not a T, it's actually, I think, the Greek symbol rho. No, it's not rho. Rho is that, right?
That's not
Well, the rho is
government follows you.
I cannot remember what Greek symbol that is, but it is a Greek symbol. Okay? It's like half of a, like taking pi and cutting it in half. So it's like taking like the rest of pi. Anyways, I don't know that out. Now, this might be the most, I don't know if I would say the most important, but it's pretty important to your ability to understand torque. Okay? It says how easily an object rotates depends upon how much force is applied. That makes sense. Okay? More force, more rotation, generally. Okay? But also where you apply that force. Now, if you think about real life situations, you might be able to make some sense to this. Any real life situation that you can think of where you push greatly affects its ability to rotate.
The door.
The door! How many of you go out that front door and push in the wrong spot?
Yes.
I do it like all the time.
Yes.
Okay? When you go out that front door, and you try to open the door, you like, guys, have you ever tried to open a door like this?
Need a lot more force.
You need a lot more what? Force to get the torque. Okay? So where you apply the force is very important for your ability to rotate. Okay? The closer you are to the axis of rotation, the more force you have to push. The further away you are from the axis of rotation, the easier it is to get the object to rotate. Okay?
So if I was trying to lift something up with a stick, if I had like a really long stick,
Yeah, it's the same as a
it'd be
ladder.
easier to-
Seesaw.
Well, yeah, that would be a different principle, but yeah, same idea. That would be your first class lever using the distance principle from physical science. Okay, anyways.
Oh, yeah.
Okay, so that's essentially, I think I just stated this, but the further the force is from your axis of rotation, the easier it is for the object to rotate, and thus the more torque that you're going to have. So then they have a little vocab word here called the lever arm. That actually is very similar to physical science. When we use lever arm to describe your first, second, third class levers and a few other things. Okay. Now let's see here. Let's say I've got some basketball. Okay. And I apply a force upward right there. Okay? My lever arm, so this would be my complete radius here. My lever arm would be from the force to the axis of motion, or the axis it's pivoting on. What's the point? Yes.
So your lever arm's perpendicular to the force?
Not always. That's why you have this sign here.
So why did you pick the radius to be right there? Why could you have done a radius at some other?
I don't know. I would just to show that the full radius isn't the lever arm always. If that makes sense. Now, if I were to apply a force right on the outside, then your lever arm would be that complete radius. It's where, just by definition, it's going to be the distance from where you're applying the force to your central pivot point. And it'll make more sense as we progress here.
It's a cat door.
Yeah, I know. They got this cat over. Cat doors don't turn. They rotate. Cat doors are for magic.
Yeah, if they don't, you're just going to slam right into the cat door.
And you also.
Oh, in that picture I thought the cat door was opening up. I'm like, I don't get it.
The cat door is open.
Well, you
No,
push
I thought it was literally just like a garage door.
Oh, garage doors don't open like this.
They open like that. That's what I'm saying. I don't get it.
You didn't see the look.
I didn't see the fact that
Some you just lift up and
It's like 1950s
they
garage
still
door.
exist.
Okay, fine. Okay.
Haven't seen Charlie Brown things.
Yeah, never again.
Oh,
I cannot watch a movie like that. I'm serious. Because what's her face?
Because they disrespect adults.
Wah, 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 wah.
There's not even adults in the movie.
No, they just say
Which one?
womp, womp, womp.
And which one made you not like?
Which one? Yeah.
Anything that has that girl in it.
Which girl?
Lucy.
The girl who's always mean.
Really?
You mean your daughter?
I would never.
You mean
Yeah, we're getting sidetracked.
You're dead. Alright.
No.
I already did that. Yes, Autumn.
What's that area business?
Which?
The one in the
blue
circle
one?
you drew. The blue.
The one you drew.
Oh, Jay.
Oh, this is referring to the force that I'm pushing on this.
Okay. What is that circle?
It's just a circle.
Like,
It's like imagine it being a volleyball, a basketball, whatever. Yeah. Okay. Now, if we're looking at this, when a cat goes through this particular cat door, not garage door opener, okay, its nose, I guess, is applying a force on that door. As it begins to rotate, it's going to have less torque because of how this cat. Well, that's it.
Can I bring in my cat?
Now it's pushing with its eye, now it's pushing with its head. Anyways. What?
Please
No.
So,
Wait,
yeah,
unless it's gray bear. Maybe gray
No,
bear.
River's a jerk.
It's not great.
I'm refraining from cat jokes just for you. Just saying.
The beast.
Getting have like cats.
Close your ears for a second.
Cats are the devil.
Okay, so all I'm trying to show you here is when you have a 90-degree angle, okay, or when you're applying a force 90 degrees to the motion, that's when you're going to have your most torque. Okay, as that angle gets smaller, you have less torque. Because if you think about it, you're getting, as the angle gets smaller, you have less and less of that force that's causing it to rotate. Okay, versus if you go perpendicular, all of that force is causing it to rotate. Okay? So as this angle starts to get smaller, the less torque you're going to have. And that's where that sine of theta comes in when you're doing your torque equation.
Wouldn't also the head getting further from the pivot point also play a factor?
Absolutely. I think they're trying to show that because it started pushing with the nose and ended pushing with the top of the head, that it was kind of the same point throughout the whole problem. But yes, if your point that you're applying a force is changing, that would absolutely have an effect too. Yes. I think they're trying in this visual to like show that the force is applied at the same location the whole time.
Yes, 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 yes.
Do it.
Yes, yes.
We only have like,
If you want to get to that problem, we have to get to the problem now. No, we're gonna skip it. We got.
Oh, you can walk over there and teach us. I don't know which button.
Okay, this is important because torque is a vector quantity, which
uh,
means you need what?
Direction.
Oh, how do you do direction for circular motion?
Around.
Is it literally like?
if it's towards the center is the direction of direction.
Okay, here we go. Torque is a vector quantity. We will assign a positive and negative sign to torque. Now again, they chose what is positive and what is negative so that it's consistent. Could they have switched them? And could you go off to physics and find out that a different book switches the sign convention? That's possible. Okay, because again, they're setting the standard so that it's consistent. Otherwise, you would have negatives in some situations and positives in other situations, and how would you know? Good question. Okay, I'm not saying that this makes logical sense, this is just what they chose, okay? So it says, they are going to, they've decided to say that a positive torque is counterclockwise. So if I'm applying a force here, which direction would it rotate?
Rotate
This would rotate clockwise, so its torque would be negative.
Wait.
Okay?
So to the right.
And they don't work out, and I'm guessing the reason why they took this sign convention has to do with the sign convention we have of forces already. And I'll explain what I mean, because you have to put the signs in your forces, and it'll work out to give you the clockwise and counterclockwise idea. Yes.
Oh wait, because you're pushing up, so it's like positive.
Yeah, it's a positive force.
Oh, that makes sense.
But so you can only
You
have,
could push up over
Yeah, why never mind.
here.
so you can only have positive and negative, not say south and.
Yes, only positive and negative, because there's only either clockwise or counterclockwise. There's no other type of rotation that you're going to get.
So that's the only direction.
So in the
that
cat-
it's a label? I thought you were gonna talk about clockwise, but like.
Yeah, or yeah, you could probably just, in this case, guys, you're probably okay just having a positive sign or a negative sign, because there's no positive is north and east. Positive is always counterclockwise.
Wait, yeah, this direction positive. Left.
Well,
Because if we go, because if it rotates to the left, it's positive.
yeah.
Yeah, okay.
Alright, so the point is here, you don't have to worry about saying clockwise and counterclockwise. You can just stay with the symbol, because it's just one thing. Yes?
If it gives us to a second word form and it says rotates to the left, where will it always be counterclockwise or clockwise?
It'll always be counterclockwise or clockwise.
Okay.
This is a tip there. Let me read it. To determine the sign of torque, imagine that torque is the only one imagine that the torque is the only one acting on the object, and the object is free. All right, that's just saying, if you look up here, you got that force, imagine which way it would rotate, you could probably figure it out. Okay.
So.
Okay, let's see the sample problem. Okay, so this one's a little bit of a tricky guy. Okay, so let's focus here, everybody. So let's just read this question out loud here, and then we'll kind of break this down, because there's a lot up here. Because a basketball is being pushed by two players during tip-off, so you can imagine a tip-off, what would happen. Okay? It says one player exerts an upward force of 15 newtons per at a perpendicular distance of 14 centimeters from the axis of rotation. Then you have a second player that I don't know why someone would ever apply a downward force when going for a tip-off, but
Spike.
anyways. Ha! Gotcha!
So you're better, you just grab it.
It's like,
I'm 8'2", I can just hit it
so
down.
what's his name, Nate Robinson, when he would just like, not even jump for it, but like went to the other side.
I don't know. Anyways, it's kind of goofy, but that's, we talk about physics and reality here, so let's be honest. Okay, the second player applies a downward force at a certain distance of.
Or like a jump ball.
Find the net torque acting on the ball load at center of mass. First thing we should probably do, since we have really two forces going on here, is we should probably draw ourselves a picture.
No, it's draw a sketch.
Kramer, what's the Q in the equation?
Q.
It's just theta, it's just the first.
Oh, yeah, that's supposed to be theta, it just got switched when it's always been.
Oh, I wrote Q on my card.
Okay, so let's say here's my center of mass for my basketball. Okay, let's just start with the first situation. It says it's applying an upward force at 15 newtons at a perpendicular distance of 14 centimeters. Now, it doesn't tell us the radius of the ball, does it? So we don't know where 14 centimeters really lies on here, so we get to kind of choose.
On the top.
It doesn't. But to make it for our visual,
He's just pushing the air really hard so it turns the ball.
yeah. So I know that maybe you don't like this, but I'm going to assume that 14 centimeters is the outside of the ball. So we're applying a force
Brains actually
perfectly on the outside of the ball here. And that force is, what do we say, 15 newtons? That's where that force is being applied. Do you want me to choose a different place?
No.
Okay, because I can't, it really doesn't
So
matter.
just the.
All you have to do is know that when you're drawing a picture, that the other force needs to be closer to the axis of rotation. Because
Yeah, you said it.
Why is it on that section? Sorry. Why not?
it doesn't matter.
Do they have to be in line with each other? Oh.
Yeah, it would. Good question.
Stop and say, buddy, just calm down.
I don't know.
It's gonna be all right.
I really don't know. I suppose, right? If it were on the other side, it would change how it rotated.
Kramer, just do the math.
Yeah.
The picture does not matter.
She's just saying, how do you know where to put it? Here's what I will assume. Just assume
It's
this.
positive, so it'd be counter. So you're right. So it'd be the other way.
I don't assume anything.
Oh, wait, never mind.
It didn't say anything about which way
Does
it's
the
rotating.
force stay positive or negative? The same way.
Yes, so it has to be an upward force, right? So it has to be upward, but she's saying, why is it not over here? That's what she's saying, and I don't know.
I like that.
Cranes, you should be the doctorates of physics.
I've never had, in my 6 years, I've never had anybody ask me that. I never had to think about that.
Lauren, you're so smart.
Wait, which one?
What
What-
do
what-
Okay, I'm afraid to say it because it'll probably just make you confused.
No, I don't care.
Okay, she's asking, why didn't I not put the force over here upward?
Wow.
Because it would change how it's rotating.
Wow.
No, I wasn't saying that was.
It doesn't say, it's on the left side of the ball and the right side of the ball.
Let's just assume that you'll say things
No,
like.
sure.
No, I was saying.
Yeah, in general,
No.
yeah, that's a good principle to look back on. See positive.
No, I
So, yeah.
didn't.
Okay, so then we got this. That distance is what? Big boys. 0.14 meters.
Wait, how do you convert that?
Yeah.
Wait, also, if we do 11 on the right side, then we just. But if we do on that side, then.
No, because it's
Down?
downward.
Yeah, so then if we do it on the right side downward, then that would just spin
Yes,
the ball.
that's the point.
But if we do it on that side, then it'll spin the ball.
Cool, they're on opposite sides. You're
Alright.
Yeah, they gotta be on opposite sides.
But he has big
He
hands.
reaches over and pushes down.
So, let's assume that our downward force is there.
No.
There.
Why isn't it?
They have to be on opposite sides of the basketball.
Has to?
Yep, they're on the same side. Because they're on tip-off.
Well, it's a tip-off. It's like a basketball
You know
game.
what
Do
that
you know what that means?
Well,
They're jumping.
Jesse!
No, that's what happens in the middle of the game.
So either way, it's gonna do tempo video.
okay, this is 0.7 meters. Okay, so we really have two torques going on here.
Shouldn't that?
Wait, there should be .07. Where's our candy? Where's the candy?
Hey, don't worry, conversions are really hard.
Sometimes that makes sense.
No,
No, it's not you. I seriously, we're just making it true. Okay, so then we really have two torques here, so your net torque would be torque 1 plus torque 2, yeah?
Okay.
Yes.
Yep. Okay, let's say that this is force 1,
Why is it capital?
and well, it's force 2.
Letter.
No, it's hard for me to draw that simple.
Well, we already have it.
They're both 90
Wait,
degrees.
so not a T.
This is supposed to probably be more like. That doesn't help. Okay, anyways.
What's the unit report?
Okay? So, we have our force, positive or negative.
Positive.
I just do this all the time. How about we do that?
Why are you doing a J?
It's not,
It doesn't, why don't you just?
it's not a T, it's not a T either.
Okay, well,
That's really long.
what is it?
The curve goes the opposite way.
Does it?
Oh,
Yes, it goes to the right, not to the left.
Oh.
Yeah.
J,
It has, why don't we just use the little T?
Oh, why did you do it like that?
that's also a T.
It's okay.
Let him write the man write. Let's do the problem.
You have to do the upper part.
I'd like
then
to.
go down, and then go down.
Okay, so, torque 1 is gonna be your force, which is a positive force.
No, it's negative.
No, it's
Upward counterclockwise.
The torque is negative.
Positive. You'll see. What is the
What
distance?
do you add?
This would be a negative.
No,
Y is a
0.21.
negative distance.
Negative 0.14. Why?
Yeah, why?
I
Why?
don't know. Because it's
Because
going
it's
to
going
the
to-
left.
Going to the
from
left of
center.
your central axis.
But that's not.
That's a scalar quantity? That's a vector quantity?
You want to call it displacement, fine.
Okay.
What do you know?
Plus,
So you always start in the center and go out from where you are?
Yeah.
Plus would be 11.
okay, your force is a negative
Because it's going down.
because it's a downward force, but your lever arm or your distance in this case is positive because it's going to the right.
0.07.
Solved. Now notice you're going to get a negative torque, which means it's going clockwise.
We're just.
Wouldn't it be cos?
I didn't understand what were all these numbers for? We're just finding.
I don't know. I think it would just be like.
What is
What is what?
Negative 2.8.
I'm guessing, looking at this, torque is a newton times a meter.
Also, why is that negative?
Which one?
I'm gonna buy you 12.
Because it's left of your center. Your force is left of
So if that was a 0, 0 on a number line,
it. Yeah.
if it's to the left.
Oh, wait. Would the end sign would still be the same if you did it the other way? Yeah.
You might be right.
Because it'd be.
No, I actually don't even know what this is.
Oh, wait.
I like some.
Let's figure it out here. We actually probably have time. What's the answer?
Negative 2.8.
No, I don't.
Is that easy? And then,
Okay, let's say we flipped everything, like we had this over here.
No, it wouldn't be the same thing. I'm lying.
You have a positive and a positive, and you have a negative.
It'd be like,
It gives you a negative.
Yeah, it would be positive.
It's not big.
That sucks.
well, yeah, because they would do something the other way.
Yeah, which makes sense. Like I said, that's why I was
with you at 7.
Oh, and because something like that.